Good morning, or good afternoon, or good evening. Welcome, everyone, and thank you for joining us for the latest episode of our Gleeble webinar series. My name is Dan Quigley. I'm the Director of Business Development and Marketing here at DSI. As always, we hope that you, your families, and your colleagues are all staying safe and healthy. As always, our goal will be to keep this webinar to 1 hour or less. If time allows, we will have Q&A at the end of the presentation. If you have questions, please submit them using the chat feature here in the webinar. We have just under 250 people registered to attend today's webinar, so we probably won't get to every question. However, if needed, we can connect you with Dr. Zheng for an offline discussion following the webinar. Video of this presentation will be available online soon. You will be able to find a link to this video as well as videos of past webinars by going to our website at gleeble.com and clicking on the resources link in the top navigation bar. Then click on webinars, and there you can sign up. You can view past webinars and sign up for future webinars. A link will be available soon to sign up for next week's webinar. I want to thank Dr. Jinghua Zheng from Imperial College London for preparing this presentation today. The title of today's presentation is Hot Forming Process Simulation, using the Gleeble for building microstructure-aided processing maps and constitutive equations. Dr. Zheng and the team in the metal forming group at Imperial College have a successful track record of developing novel metal forming processes, and Dr. Zheng will present her work using the Gleeble to simulate the hot stamping process of an aluminum alloy. The presentation will include case studies, including the identification of high temperature transfer effects during hot stamping on microstructure and mechanical properties, building processing maps for property control of hot stamped components, and material modeling based on both viscoplastic behavior and associated microstructures. Dr. Zheng, I'll now hand this over to you, and thank you again for sharing your work with the research community. The floor is yours.
Hello, welcome everyone to attend this webinar. And my name is Jinghua Zheng, coming from Imperial College London. It's really my pleasure to be invited to give a talk today. The topic today is hot forming process simulator, using Gleeble for building microstructure-aided processing maps and constitutive equations. So before directly go to this topic, let me first introduce my university, Imperial College London. So our university is a relatively small university containing around 70,000 students and around 40,000 staffs. And it is a really international university, and around 60% of the students and 40% of the staff are coming from outside UK. Regarding the ranking, it has a good reputation. It's ranking the 3rd in UK, 3rd in Europe, and 8th in the world according to QS rankings. So this picture shows the South Kensington campus of Imperial College London, and the South Kensington campus is this part. So basically, it locates in the center of London. If you see this white tower, so this is called the Queen's Tower. It is the symbol of our university and the engineering faculty building, and also the mechanical department is just next to the Queen's Tower. So regarding the location, it is quite good. It's just next to the hydro park, and you could feel free to go for relaxation after 1 day's tired work. And also besides it have Victoria Museum, Science Museum as well. So if you got a chance to visit London, it would be a great choice if you come to Imperial College, and I'm sure you will leave a fantastic memory here. So regarding the Department of Mechanical Engineering, we have 3 divisions: applied mechanics, mechanics of materials, and also the thermofluid. So we have 60 academic research staff, including 4 fellows of the Royal Society, 8 fellows of the Royal Academy of Engineering. So I'm based in the division of mechanics of materials and in the metal forming and the material modeling group. So this group is led by Professor Jinghua Zheng, who is the head of the department and also one of the Royal Academy of Engineering, the fellows of Royal radioacademic engineer, and I think he already gave a presentation in June or July, and regarding our group. The main work is the metal forming process, including the traditional forming process, including forging, extrusion, heat treatment, residual stress, etc. And also, we concentrate on building hybrid process. For example, the hot stamping and cold die punching for steels and aluminiums, the pre-page forming process, which is able to control both the formability and also the post-form mechanical properties of the part. So for the testing facilities, we have the Gleeble 3800. We also have a range of hydraulic presses for forging, sheet metal forming, etc. Okay, so now let's go to this topic. So no matter for traditional forming process or hybrid process, so basically what we want is the high formability during forming with no crack happens, and also we want the good property after forming process in service, such that the component could have high performances. So these two key aspects is related to the stress strain curves at the different temperatures and different strain rates. We call it material flow behavior, and also it relates to the microstructure evolution during the forming process, such that we could have the desired microstructure and also desired mechanical properties afterwards. Okay. So one of our group's expertise is to building the physically based, evolutionary based constitutive equations, which is able to accurately describe the stress strain curves, and also this description, this constitutive equation could be embedded into the FE simulation, such that the full component could be predicted regarding the thickness distribution of the part, the microstructure evolution and distribution of the part, the mechanical property of the part. So this is an example. It is a door inner of the automobile. So our group is continuously performing research to improve the constitutive equations, and also it is one of my major work as well. So we are trying to get improved version which could capture the main viscoplastic flow mechanism of the material and incorporating the key microstructure evolutions. For example, the dislocations, damage evolution, recrystallization evolution, etc. So today, my topic is mainly focused on the hot stamping and cold die punching for aluminium alloys. And of course, this part is mainly based on the Gleeble-aided experimental work, including the stress strain curves and also the microstructure examination during the stress strain curves. So I'm going to talk about how we use the Gleeble to building the processing maps and to aid our microstructure understanding and microstructure evolution during this process, and how we base on the microstructure to improve the constitutive equations. So I'm going to give 3 case studies here. Starting from the first one is building blank transfer processing map for 6082 and 7075 for HFQ hot forming processes. So regarding the hot form and quench, we also call it HFQ. So this technique is developed by Imperial College London, and currently this technique is being used especially for forming high-strength aluminium alloy to achieve the complex geometry components. And currently it is being used in the automotive industry. So let me first introduce this process briefly. Initially, the material is aluminium blank, no matter whether the condition is. And what happens later is that we heated the material to the solution heat treatment temperature, which fully solutionized any of the precipitates inside of the blank. And later, the part will be transferred to a cold die, during which the temperature will be dropped due to the transferring. And once the part is transferred, and a cold die will be applied on the hot blank to enable both forming and quenching of the components. So after this part, the required geometry of the part is achieved, as well as we achieve the supersatural solid solution of the part. So this part will finally goes into a furnace to enable H-hardening response and to trigger precipitation process to improve the mechanical properties of the part. So this topic is mainly focused on the blank transfer effect and trying to build a processing map for the blank transfer control to give indications for the industry. So why blank transfer is important? If we look at this temperature profile according to the hot stamping, hot form, and quench process, so what happens is during transfer of the blank, the temperature will be dropped at a certain time. So what happens is for aluminium alloy, one of the essence is to control the C curve of the part. So basically, if the material is holding at a very high temperature for a specific time, the final mechanical properties after aging will be deteriorated. For example, hold it for some time and the final mechanical property will be reduced to 99% and then reduced to 90% and then later to 80%, etc. So why this happens? This is because the formation of coarse precipitates due to the high temperature soaking process. So basically what happens if you look at the stage 2 and stage 3, regarding this is the schematic drawings of the microstructure, stage 2 and stage 3. So what happens is big coarse precipitates will be formed, and for 7 series we call it eta precipitates, and these precipitates will occupy the element. So after aging, so it will reduce the final mechanical properties of the part. So understanding this mechanism, so our aim is to quantify this effect and trying to build the processing map for better property control of the final components. So given the aims of this subject, this is the temperature profile we built. So basically, according to the hot stamping process, hot form and quench, we heated up the material to the solution heat treatment temperature, and then quench it down, start cooling it down to different temperatures from 250 to 400, and then we hold it for 1 to 10 seconds at the specific temperature according to the industry requirements, and then later using water to quench the material further. So what we did is that we did the TEM, the transmission electron microscopy, directly afterwards quenching, and also after the artificial aging to look at the microstructures. At the same time, we conducted the tensile and hardness test after the aging, trying to building the processing map for the transfer process. So of course, the machine we used is Gleeble, and I think Gleeble is the machine to accurately simulate the whole process and giving the accurate control of the temperature profiles that we designed. So this is the samples that we used, and for tensile test, because we know that for Gleeble we have a temperature distribution in the longitudinal direction. So we measured the temperature distribution at a different point of the specimen, and finally we machined out the very small tensile specimen from the big specimen, which have the uniform temperature distribution around 5 degrees, within 5 degrees C. So this is used for building the processing map for the blank transfer stage. Okay, so this is the brief microstructure results. So here is the TEM image directly after water quenching, and the holding temperature is 350, lasts for 5 seconds, and 350 lasts for 30 seconds. So you could see like very big precipitates were formed. It's larger than around 100 nanometer, and with lengthening the holding time, we could see like bigger precipitates with higher volume fraction was achieved, which is expected to damage the final mechanical property of the part. So let's look at the microstructures after aging. So these TM image are the microstructures after the artificial aging treatment at 3 different temperatures, 300 degrees C, 350 degrees C, and 400 degrees C. And the soaking time is both 10 seconds. So what we can see is that for 330, we have very large grain boundary precipitates, and we also have big precipitates inside of the bulk matrix. So this precipitates occupies the elements. So if we look at the main strengthening phase, the small precipitates in the bulk matrix, we could find that low volume of the fine precipitates were formed compared to to other temperatures. So from these slides, we understand, or the conclusion we got is the most sensitive temperature, soaking time temperature, is 350, and we have due to the large grain boundary precipitates, so the volume fraction of the effective small precipitates becomes smaller. Okay. So these slides, after the microstructure examination, these slides gave the final processing map that we achieved for 7075, and this is for the 6082. So as I described in the earlier slides, the safeguards are very important for the property control of the part. So what we could see is that lengthening the holding time of the material will reduce the final mechanical properties of the part. So conclusion is based on accurate temperature control from Gleeble, we are able to build the blank transfer window for 7075 and 6082, which could give indication for the industry how to select the best transferring temperature and time for their components. So the most sensitive, we call it nose temperature, is 330 for both 7 series and 6 series aluminium alloy. And if we look at the horizontal axis, for 7 series aluminium alloy starts from 0.1. So if our transferring time is transferring temperature is 350, and after probably 1 second soaking, it will reduce around 10% of the final mechanical property. After 10 seconds, it will reduce around 20%. But for 6 series, it starts from 1 second. So that means for 1 second soaking at 330, it won't affect much of the mechanical properties. So that means for 7 series, it's much more sensitive material that need to take more care of this material for forming process, and much more sensitive than 6 series aluminium alloy. So this is the brief description of this work. So if you are interested, and you could find details in this paper. Okay. So last case, we described the how we built processing maps, and for case studies 2, we are going to focus on quantify the dislocation density of the Gleeble deformed AA6082. It is mainly focused on microstructure examination during the forming process. So again, given the HFQ process previously we focused on transfer, and now we focused on the forming process. So what happens is for forming, because we form the material at a reduced temperature, so we never know how much dislocation density were created. And the dislocation density is very important because it is the essence for the plasticity of the material and also governs the viscoplastic behavior of the material. So this topic will focus on quantify the dislocation density during forming, and also another significance of this work is currently we got two sets of model. One is called the continuous damage model, which is able to predict the stress strain curve during forming. And the other is called the aging model, so which is able to predict the precipitation process after the forming. However, during forming, because we have the high temperature residual dislocations, so these dislocations will affect the age-hardening behavior of the material. If we do not have this set of data, we could not link the two existing models together to create an integrated model for both the deformation and also the property control of the components. So this is why we are working on how many dislocations are created. So based on such aim, what we defined is again the temperature profile, and this process, this experiment is also based on Gleeble, which could accurately control the temperature and strain rates of the components. So again, this is the temperature profile heated to the solution heat treatment temperature, and then quenched to three different temperatures, 300, 450, and 500 degrees C. And also we deform or stretch the material using three different strain rates to different strain levels, and later we quench it down using the Ebsd examination to examine the microstructure distributions after the forming, and also to look at the microstructure evolution during the forming. So this is the sample we got, and this area, the Ebsd area, is located in the middle of the specimen within the uniform temperature and deformation area, such that we could guarantee the reliability of the testing. Okay, so given such test metrics, regarding the first matrix is looking at the temperature effect. The first row is the temperature, the recorded temperature during forming, and this is for deformation at 530, at 450, and also quench it down to deform at 300 degrees C. The second row is the stress strain curves under the same conditions. So basically, material is stretched to different true strain levels and then stop the test. So if you could see is that we did a repeatability test, and you see like two different or three different curves that coincide with each other, which ensure the reliability of the test, and also gave a sign that Gleeble could accurately control the temperature and also give repeatable stress strain curves at the required conditions. Okay, so having done the Gleeble test, we examined the Ebsd image of the different treated specimens. So these are the Ebsd resolved geometric necessary dislocation density map. You could see the color of the map. If the color turns from the cold color to the hot color, so that means the dislocation density increases. So if you look at these 6 maps at higher temperature, the color of the map is blue, and when we reduce the deformation temperature, it turns from blue to the yellow and the red one, indicating the increase of the geometric necessary dislocation density. So we also quantified the statistically meaningful GND density with respect to true strain levels at the 3 different temperatures. And this is the quantitative result that we hope to get corresponding to the stress strain curve point A, B, C, D, E, F. So regarding the test metrics too, we fix the temperature and then we look at the strain rate effects. And again, the first row is the temperature, and the second row is the stress strain curves and the different strain rates. So if you could see that reducing the strain rate will increase the deformation time of the components. So if you look at the temperature with respect to deformation time, the strain rate 0.01 per second, it lasts very long, but strain rate 1 per second is only deformed within seconds. So giving such data, and later again we examined the Ebsd results, and the point A, B, C, D, E are corresponding to the maps 1, 2, 3, 4, 5, A, B, C, D, E here. So as expected, increasing the strain rate will increase the geometric necessary dislocation densities as the deformation time is shorter, and there will be shorter time for the recovery of the dislocation densities. So this is the final map that we built. Is the GND density with respect to true strain levels at 3 different temperatures, and the GND densities with respect to true strain levels at 3 different strain rates. So these are expected to be used to calibrate the constitutive equations that we obtained, and also it should be noted that it's based on assumption that geometric necessary dislocation density could represent the trend of the total dislocation density. And under that assumption, this data could be used. And currently, for microstructure examination, our work just stopped here, and the building of constitutive equation is now under preparation. So for case study 2, we got the overall GND has been quantified, and also they are statistically meaningful. And the second is we observed the dynamic recrystallization and observed the grain size evolution as well. So they are all based on accurate temperature and deformation control from Gleeble. So this work is formulated into a paper. Currently is under review, and will, if you are interested in this work, and you are more than welcome to keep an eye on the coming publication. So that is case study 2. And regarding to the case study 3, I'm going to give a full story of how we use the microstructures to aid the improvements or building of the constitutive equations for forming process at elevated temperature. So as I just talked about the essence of the aluminium alloy is this C curve. So if a temperature is defined to go into the C curve, that means coarse precipitates will be formed, which is detrimental to the final property. So based on this understanding, we proposed another forming method, which is called fast forming. So we hope to fastly heat up the material to a temperature, and then we form at this high temperature, and later we quench it down very fast to avoid entering the C curve of the components, such that the material formability could be achieved at high temperature. and also the post-form mechanical property could be retained. So once this method is created, we hope to check the feasibility of the process, and also we hope to model the process regarding the viscoplastic behavior and mechanical properties. So based on that newly proposed method, what we did is we again using the Gleeble to heat up the material using different heating rates, and then we soak it for 1 second to stabilize the temperature. And later we conduct the hot tensile test at the designed temperature. So we examined the microstructures at the initial stage, and also after directly heating without deformation, and again after the deformation. So these are the this is just a part of the microstructure results. One is TM results, and the other is Ebsd. TM is looking at the precipitates, and Ebsd is looking at the grain distributions and also the geometric necessary dislocation distributions. So this two is regarding to the initial process, initial of the material, and this two is regarded to the microstructure without deformation, and this one is microstructure with the deformation. So I'm not going to talk about much details of the microstructure. So based on the microstructure analysis, what we built is an improved set of constitutive equations, which is able to describe the viscoplastic behavior and also the mechanical property evolutions during the forming process. So these two are all based on the microstructure internal variables and including the precipitates, the radius of the precipitates, how it evolves, the solute concentrations of the precipitates, the dislocation density evolutions, the dynamic recrystallizations, and also the grain size evolutions. So these three boxes, they are interactively related to each other because microstructure evolution will both affect the viscoplastic behavior and also the mechanical properties. So based on such set of microstructure-based constitutive equations, it have been calibrated and able to describe the stress-strain curves, the hardness evolution, the microstructure evolutions as well. So if you look at this slide, the first row is the viscoplastic behavior and the different heating rates, and at different deformation temperature, and also at different deformation strain rates. The solid curves are the computational one, and the symbols are the experimental one. So relatively good agreements were achieved. And the second row shows the hardness with respect to the heating temperature at different heating rates. And the second is the precipitate radius with respect to the heating temperature. And the third one is the normalized value, the volume fraction, and the solute concentration with respect to heating temperature. So if we take a detailed look about, of the hardness, for example, if the final part, what the industry could be accepted is 80% of the 80% of the T6 material. So that T6 is the peak aged material. So in that case, for the heating rate of 5 degrees per second, the deformation temperature could be up to 280. And for the heating rate 1 degree per second, and the deformation temperature could only be around 220 degrees. So based on such constitutive equation and also the calibration of the model, and now gives the conclusion. So basically, with the simulated temperature and deformation control from Gleeble. Firstly, we built a constitutive model which is able to describe the hot flow behavior, the stress evolution, and the microstructure evolution. The second is we examined the heating rate effect on the final mechanical properties, and also the heating rate effect on the flow stress behavior at different temperatures and strain rates. So the details of this work is also could be found in this paper below. So after giving this 3 case study, let's go to the final conclusion. Is firstly, the design mechanical process, thermomechanical process could be accurately simulated using Gleeble to help building the processing map, the microstructure analysis, and helping to build the microstructure-aided integrating model development. The second conclusion is that our group and myself has long-standing interest in building evolutionary physically based constitutive equations for various forming processes. And these constitutive equations could be embedded into the FE simulation to determine the optimized processing windows for the designed forming processes and able to predict the formability, property, and microstructure evolutions. So thanks, this is the end of my presentation, and I'm the presenter, Jinghua from Imperial College London. And today my presentation is mainly related to Gleeble work, which is one part of my my research work. So for myself, I'm also interested in the residual stress measurement and control and new hybrid process development. So if you are interested in any of the this area, you are more than welcome to drop me an email, and then we could discuss further, probably for future collaboration. Thank you. Any questions?
No, thank you. This was great, a great presentation, and we do appreciate it. And I'll also say that I think you're our first presenter that was exactly on the time that you said your presentation would be. So great job. We do appreciate it. And so we do have a few questions that have come in, and so I'll try to read them here, and hopefully I can convey them okay. And if we need to, I can send them through in the chat as well. First question here, it said, referring to case study 2, in the hot form and quench test, how do you choose the true strain? And the attendee said, I think the true strain values are chosen during the test before the specimen reaches the ultimate point in the tensile test. Is this correct?
Yeah, that's correct. For the true strain is first we So first we stretch material until it's failure, and then we just select the 2 points of it, the 2 representative point, and then stop it and to look at the microstructure evolutions during the test. Yeah.
Great, thank you.
Yeah,
Okay, another question regards to this case study 2. It's after hot stamping and quenching, the deformed sample is subjected to artificial aging. During artificial aging, is there no distortion in the deformed component?
Oh, sorry, could you repeat again? No distortion of the...
Yeah, so during the artificial aging, is there distortion in the deformed component? So is the component is it distorted?
No, there is a slightly deflection of the part, but it's negligible. From the industrial feedback is that as long as we just stack all the components and directly go into the furnace, as the artificial aging, the temperature is low, and also the thickness of the part is very thin. So there wouldn't be much of the distortion issue that concerned by the industry. The final geometry will be as required.
Okay, and then a follow-up question, I suppose, to that one. It says, how do you distinguish the effect of lattice dislocations from GND in the Ebsd?
The lattice dislocations.
Yes. So
yeah.
Yeah. So it's
sorry.
Yeah. Like me to repeat the question. It says, how do you distinguish the effect of lattice dislocations from GND in the Ebsd?
Oh, okay. Currently, we have the MTEX, which is developed. I think is ready to use in the website, and we are currently one of the group who is using this one to calculate the GND dislocation density. But regarding the lattice dislocation, I'm not very sure about it.
Okay.
Yeah.
Fair enough.
Yeah.
So again, on case study 2, it said, I see that you vary both the strain and strain rate at a fixed temperature. If so, how do you know the contribution of each, meaning strain and strain rate, on the dislocation density?
The strain and strain rates, they are combination effects. So if we look at this one, so because for strain rates is also depends on how long time we soaked the material or deformed the material. So what we attribute for the dislocation density is how much deformation time that's required for the deformation, and what is the deformation temperature for the GND density. So that is how we considered the case.
Great.
Because for different strain rate, you deform the material, the time for you to deform the material is longer or shorter. So that means the soaking time or the deformation time is different. So the two major contributors is the temperature and also the soaking time for the material.
Okay, great.
Yeah.
So this one, I'm not sure which case this is referring to. It says, is the contribution from precipitation hardening also included in the model? They said, I didn't the interparticle distance, particle size, and type of precipitates formed in the study.
Yeah, I think it's a study trait. So basically, we have the key microstructures, the contribution of precipitates. We considered the radius of the precipitates during the radius evolution during the deformation, the solute concentration evolution during the precipitation, and also the volume fraction evolution of the precipitates during the deformation. So these are the first one, the second one, and the last one is related to the precipitate evolution and its contribution to the mechanical properties and the viscoplastic behavior. Yeah.
Okay, great. So we do have a few more questions here. So let's, in sheet specimens, to ensure accurate flow stress computation, do you use strain gauge at the uniform temperature region?
Yeah. What we did is we used the C gauge. So just a minute. We used the C gauge to measure the displacement in the lateral direction, in the transverse direction, so that we could directly achieve the strain levels from the detected C gauge. Yeah. So these are coming from the C gauge measurements.
Okay.
So that's why, we could not control the true strain rate to all be 0.1 or 0.3. It depends on how much true strain we measured from the C gauge. So it's slightly varied. For example, this is 0.08, 0.01, 0.13. So it's roughly in this range.
Okay.
Yeah.
A few more here. With respect to case study 2, could you comment on whether similar methodology can be used to perform Gleeble experiment and measure dislocation density for steels as well?
I think so. Currently, I think this is the best method to measure the dislocation evolution, especially at the high strain rates, because we could not do the in situ test at such strain rates where deformation happens within seconds. So as long as you could crunch it down and look at the microstructures at different strain levels, and then you are able to get the microstructure evolutions during the deformation. We call it the quasi in situ test to achieve the microstructures during the forming. Yeah.
Okay, great. And then we had a few questions again about other materials as well. So, and I know you spent a lot of time here on obviously on aluminum, but have you? Yeah. Is this model applicable to other materials? And in particular, someone did ask about hot forming of high entropy alloys.
High entropy alloys, I do not have much experience in it, but I think this method is applicable to most of the metals as long as you have the correct way to measure the microstructures and the dislocation densities, then should be fine.
Yeah, and I agree. I think I'm sure we have a lot of Gleeble users out there that are doing this, and I'm sure that if they were unmuted, they would chime in and agree that similar models can be applied. So thank you. I think there's one final question here. I know you've been answering a bunch of questions. So have you observed any initiation of voids at a higher true strain, like, and they say 0.43? So initiation of voids at higher true strains.
Yeah, one of the thing that we are concentrated is also the voids, the damage evolution during the process. But based on the the result from our group is that as long as the deformation level is less than half or less than 60% of the fracture strain, then the voids will not become a very big issue. But once the deformation level is up to probably 80% or 70%, and then we should consider the voids formation and the damage formation as well. But from this set of the data, we didn't see much of the. We didn't, honestly speaking, we didn't see the voids from the deformed material. Yeah, because like the deformation level is all within 50% of the fractured strain levels.
Great, thank you. So I want to thank, we had a number of great questions today. I want to thank the audience for asking those questions and for everyone's attention. So we'll kind of wrap this up here. And again, Dr. Zheng, I want to really thank you for taking the time. I know it's a lot of time to prepare these presentations, and we do appreciate it. If anybody would like to reach out to you or make a connection, please, they can email me, and I can make that connection if you'd like to make that introduction. If anybody does have questions about more technical operations of their Gleeble, we're here to help. So please contact our service team. I've mentioned this in previous webinars. We do have that service portal that's available on our website. There's a knowledge base there. You can also search for some answers. You can access that by going to that resources tab on our website and then go down to the customer support portal. If you're a current customer, you can sign up and we'll get you signed up there, and you'll create an account and you'll be able to ask questions and search the database. That's the best way to get kind of a first level of support, and then our team can assign that to the right person to get back to you. If you have questions about how Gleeble can support your research, please email me or anyone on the Gleeble team here. We're happy to help to connect you with an application expert to help you find the right solution. I think everyone has my email address. They're in the invites. It's dan.quigley@gleeble.com. Please feel free to reach out to me. I do look forward to hearing from you. I want to thank everyone for joining us. I want to hope everyone stays safe and healthy. And Dr. Zheng, again, thank you for the presentation.
Yeah, thank you all for attending, and you are more than welcome to contact me if you have further questions or if you are interested in this research project. And also thank you, Dan, for organizing this wonderful